Occam's razor. The more complex an explanation is, the more evidence you need just to find it in belief space. In traditional rationality, this is often phrased misleadingly as the more complex a proposition is, the more evidence is required to argue for it. How can we measure the complexity of an explanation? How can we determine how much evidence is required? Occam's razor is often phrased as the simplest explanation that fits the facts. Robert Heinlein replied that the simplest explanation is, the lady down the street is a witch. She did it. One observes that the length of an English sentence is not a good way to measure complexity, and fitting the facts by merely failing to prohibit them is insufficient. Why exactly is the length of an English sentence a poor measure of complexity? Because when you speak a sentence aloud, you are using labels for concepts that the listener shares. The receiver has already stored the complexity in them. Suppose we abbreviated Heinlein's whole sentence as tlizvardi, so that the entire explanation can be conveyed in one word. Better yet, we'll give it a short, arbitrary label like fnord. Does this reduce the complexity? No, because you have to tell the listener in advance that tlizvardi stands for the lady down the street is a witch, she did it. Which itself is a label for some extraordinary assertions. Just because we all know what it means doesn't mean the concept is simple. An enormous bolt of electricity comes out of the sky and it hits something, and the Norse tribes folks say, maybe a really powerful agent was angry and threw a lightning bolt. The human brain is the most complex artifact in the known universe. If anger seems simple, it's because we don't see all the neural circuitry that's implementing the emotion. Imagine trying to explain why Saturday Night Live is funny to an alien species with no sense of humor. But don't feel superior, you yourself have no sense of fnord. The complexity of anger, and indeed the complexity of intelligence, was glossed over by the humans who hypothesized Thor the Thunder Agent. To a human, Maxwell's equations take much longer to explain than Thor. Humans don't have built-in vocabulary for calculus the way we have built-in vocabulary for anger. You gotta explain your language, and the language behind the language, and the very concept of mathematics before you can start on electricity. And yet it seems that there should be some sense in which Maxwell's equations are simpler than a human brain or Thor the Thunder Agent. There is. It's enormously easier, as it turns out, to write a computer program that simulates Maxwell's equations compared to a computer program that simulates an intelligent emotional mind like Thor. The formalism of Solomonov induction measures the complexity of a description by the length of the shortest computer program which produces that description as an output. To talk about the shortest computer program that does something, you need to specify a space of computer programs, which requires a language and interpreter. Solomonov induction uses Turing machines, or rather bit strings that specify Turing machines. What if you don't like Turing machines? Then there's only a constant complexity penalty to design your own universal Turing machine that interprets whatever code you give it in whatever programming language you like. Different inductive formalisms are penalized by a worst-case constant factor relative to each other, corresponding to the size of a universal interpreter for that formalism. In the better, in my humble opinion, versions of Solomonov's induction, the computer program does not produce a deterministic prediction, but assigns probabilities to strings. For example, we could write a program to explain a fair coin by writing a program that assigns equal probabilities to all 2 to the nth strings of length n. This is Solomonov's induction's approach to fitting the observed data. The higher the probability a program assigns to the observed data, the better that program fits the data, and probabilities must sum to 1, so for a program to better fit one possibility, it must steal probability mass from some other possibility, which will then fit much more poorly. There is no super fair coin that assigns 100% probability to heads and 100% probability to tails. How do we trade off the fit to the data against the complexity of the program? If you ignore complexity penalties and think only about fit, then you will always prefer programs that claim to deterministically predict the data, assign it 100% probability. If the coin shows heads, tails, tails, heads, heads, tails, then the program that claims that the coin was fixed to show heads, tails, tails, heads, heads, tail tails fits the observed data 64 times better than the program which claims the coin is fair. Conversely, if you ignore fit and consider only complexity, then the fair coin hypothesis will always seem simpler than any other hypothesis, even if the coin turns up heads, tails, heads, heads, tails, heads, 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 tails, heads, 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 tails, heads, 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 tails. Indeed, the fair coin is simpler, and it fits this data exactly as well as it fits any other string of 20 coin flips, no more no less. But we see another hypothesis, seeming not too complicated, that fits the data much better. If you let a program store one more binary bit of information, it will be able to cut down a space of possibilities by half, and hence assign twice as much probability to all the points in the remaining space. This suggests that one bit of program complexity should cost at least a factor of 2 gain in the fit. If you try to design a computer program that explicitly stores an outcome like heads, tails, tails, heads, heads, tails, the 6 bits that you lose in complexity must destroy all plausibility gained by a 64-fold improvement in fit. Otherwise, you will sooner or later decide that all fair coins are fixed. Unless your program is being smart and compressing the data, it should do no good just to move one bit from the data into the program description. The way Solomonoff induction works to predict sequences is that you sum up over all allowed computer programs. If every program is allowed, Solomonoff induction becomes uncomputable, with each program having a prior probability of a half to the power of its code length in bits, and each program is further weighted by its fit to all data observed so far. This gives you a weighted mixture of experts that can predict future bits. The minimum message length formalism is nearly equivalent to Solomonoff induction. You send a string describing a code, and then you send a string describing the data in that code. Whichever explanation leads to the shortest total message is the best. If you think of the set of allowable codes as a space of computer programs, and the code description language as a universal machine, the minimum message length is nearly equivalent to Solomonoff induction. This lets us see clearly the problem with using "the lady down the street is a witch, she did it" to explain the pattern in the sequence 0101010101. If you're sending a message to a friend trying to describe the sequence you observe, you would have to say, "The lady down the street is a witch, she made the sequence come out 0101010101." Your accusation of witchcraft wouldn't let you shorten the rest of the message. You would still have to describe in full detail the data which her witchery caused. Witchcraft may fit our observations in the sense of qualitatively permitting them, but this is because witchcraft permits everything, like saying phlogiston. So even after you say witch, you still have to describe all the observed data in full detail. You've not compressed the total length of the message describing your observation by transmitting the message without witchcraft. You've simply added a useless prologue, increasing the total length. The real sneakiness was concealed in the word "it" of "a witch did it." A witch did what? Of course, thanks to hindsight bias and anchoring and fake explanations and fake causality and positive bias and motivated cognition, it may seem all too obvious that if a woman is a witch, of course she would make the coin come up 0101010101. But I'll get to that soon enough.